Okay, hi friends. In this video, I'm again going to answer a question that was raised in the class, but due to short time, I couldn't give complete answer to. So the question is that it's as follows. So we started the series parallel equivalence of inductance. Say if we have a series resistance Rs combined with a series inductor Ls, and if I compute the impedance of this, I can always find an equivalent combination of Rp and Lp such that the impedance of these two are same. And if I now do the computation, it's actually fairly simple. So I start with, say, Zs for impedance for this circuit, which is Rs plus j omega Ls. So Ys, the admittance, will be the reciprocal of this, which is in turn equal to Rs minus j omega Ls by Rs square plus omega square Ls square, and these two circuits to be equal, this should be equal to Y parallel. So admittance of this circuit, so this should be equal to this Rs square plus omega square Ls square minus j omega Ls by Rs square plus omega square Ls square, and this Yp is equal to I have 1 by Rp plus 1 by j omega Lp, which is same as if I take this j in the numerator, I will have a minus j by this. Now if I equate real to real and imaginary to imaginary parts in this equation, I get, so this implies Rp is equal to Rs plus omega square Ls square by Rs, and here I have omega Lp is equal to this, so that means Lp will be equal to Rs plus omega square Ls square divided by omega Ls, and there is omega, so there will be omega square. So I will end up with this equation. Okay, and as one of our friends have already observed that this transformation depends, this equivalence holds on the for a particular frequency, or in other words, this transformation from Rs Ls to Rp Lp depends on the frequency. What does that mean? So it means the following. Say I start with I do the following experiment. Let me do the following experiment. So I first start with pure Ls and Rs, okay, and then find equivalent Lp and Rp, okay, and then make the circuit. Third step, make the circuit. So this is Rp and this is Lp, and once I make the circuit, so I have computed these two for a particular frequency, say omega 1, and then I have made this circuit, and then next I measure this Rp and Lp. So measure Rp and Lp at another frequency omega 2. What I will find that the measured value of Rp and Lp is not same as what is computed through this equivalence. So this is the problem. uh, yeah, and therefore the bigger question that can be raised is this: since I started with RL and LS as with pure RS and LS, and then I found the equivalent, and then I observed that this equivalence is no longer true when I change the frequency. However, this series series circuit is not changed with the change of frequency. What I mean by that is that if I make this circuit with RS and LS and apply a different frequency across it with frequency omega 2, what I'll find that the inductance and resistance, they are still LS and RS. Does that mean that this series equivalent circuit is more reliable or is better in some sense because it's not dependent on the frequency, whereas the parallel equivalent circuit, this depends on the frequency? So this is the bigger question: is series circuit better than parallel equivalent? So this is the real question which I'm going to talk about. And the answer is, let me first tell you the answer. The answer is no in general. In this experiment, we started with pure RS and LS, ideal RS and LS, and then we made this series combination. But in practice, there is no, almost in many cases, there is no pure RS and LS, or no, there might be inductors which cannot be thought of as a series equivalent of RS and LS. Why? In the class, I told that this RS comes in series with LS because of coil resistance. And intuitively this is clear that if it is just coil resistance, then this is the physically correct circuit to have them in series. However, this RS is not just the coil resistance, but there are other factors as well. Let me just mention some of them. Let us assume that we have an iron core. Let's think of an iron core inductor. So this is an iron core inductor. Now, if I apply a voltage across it, I will say this conductor is made of superconducting material. So there is no I square R loss involved at all. But now, if I measure the voltage and the current through it, what I'll find that this voltage and this current, they are not at 90-degree phase shift. So if this is the voltage, the current is not here at 90-degree. So this is not the case. Rather, I shall find the current to be here. So why this is so? This is because this system has some energy loss associated to it, which is in the form of the eddy current generated in the core, the hysteresis loss in the core, due to hysteresis, the flux of in this magnetic circuit won't be at the same phase as the current, rather it will lag the current, and therefore the voltage won't be at 90 degree with the current, but will have an angle less than 90 degree. And so this less than 90 degree angle also signifies that there is an active component of current, which signifies the consumption of power in this circuit. And this consumption is not due to the I square R loss, and because we are assuming this is made of superconducting material hypothetically. But still we can make an equivalent RL model of this circuit, and that can be either this series circuit or the parallel circuit we have. Both of them ensures that the voltage and current are not at 90 degree. For example, in this case, so I know if this is current, so there is an IR voltage, so VR times VL, and this is the resultant. So the angle is less than 90 degree. Now here as well, if I consider the V here, then there is a current at, so this is V, this is IL, and there is a current IR. So once again, V and I are not at 90 degree. So both of them are fine to to represent my observation which I experimentally have found. But once again, I don't know which is here is the correct representation, because this is not coming from any physics which says that this is the coil resistance which should come in series with the inductor, but this is coming from the observation that there is a loss of power which should make the voltage, the angle between voltage and current less than 90 degree, for which I should either have a series resistance or a parallel conductance, and either is fine to explain my observed behavior between voltage and current. So if I look from outside, I cannot distinguish between this circuit and this circuit. But this is true only for a particular frequency. Why? Because this AD current and hysteresis loss both depend on frequency. For example, it's easy to see as the frequency increases, the rate of change of flux increases, and thereby the voltage generated in the core will be more, and the eddy current will be more. So the eddy current loss will be more as the frequency increases. Similarly, when frequency increases, the lag of flux from the current. So the flux. If this is current, if this is flux, this angle, the lag of flux from the current, that also increases as the frequency increases. Therefore, the amount of energy lost completely depends on the frequency, and thus, just by observing this energy loss, if I model it as an LS or RS, that is valid only for a particular frequency and not for any other frequency. And thus, the bigger question that we raised, whether the series equivalent circuit is a better representation than parallel equivalent circuit, it's not. Let me end this video with a mention that this is also true for capacitors. So we talked about capacitors, and we said since the dielectric is lossy, we can think of a small conductance around. But it also has a lot of losses associated with it. One is of course the I square R loss, so when current flows through the leads or through the inside the plate, there is an I square R loss. There is a dielectric loss associated to it, which is due to constant polarization and depolarization or opposite polarization of this dielectric material. So the voltage applied across this dielectric chain oscillates, and therefore the polarization also oscillates. So the molecules needs to move, which causes some energy to be lost in the form of heat. And all these observation, when looked from outside, can be modeled as either a parallel equivalent or a series equivalent, but there is no physical interpretation which says that the parallel equivalent is correct or series equivalent is more correct. This is only correct for a particular frequency and not for any other frequency. Thanks.